Excellent. Thank you so much for having me. I'm excited to share this work for you. And okay, so I'm going to be talking today about using an online sample to learn about an offline population. And this is a joint paper with Curtis Cobb, who's at Facebook. So I thought I'd start by trying to talk a little bit about the big picture problem that this work is going to try to help to address. And that's a situation many social scientists, I think, will recognize, which is that we're interested in in understanding something about a population, but for some reason it's difficult to sample and interview members of this population directly. It might be that people in this group are difficult to reach for some reason, or it might be that it's very expensive to sample and interview them. There might be no readily available sampling frame. A lot of reasons why this might happen. But it's often the case that there's some related group that we can potentially sample and interview considerably more easily. So that might be people who use the internet, who have mobile phones, who visit a website, et cetera, et cetera. And the idea is to try and understand how we can take a sample of people from this easier to access group and learn about this broader population of interest. And the big picture idea is that everybody is connected to other people through various kinds of personal networks. So that might include friends, professional colleagues, family members, et cetera, et cetera. So we can sample people who are in this easier to reach group and ask them questions about others who they're connected to through these different kinds of personal networks. And that gives us some information about a broader set of people than just the folks we can directly talk to. So this isn't going to be an approach that is right for every single problem that has this structure, but I think for some problems with this structure, this is an approach that can be really promising. And so I hope the talk today will kind of help to describe a little bit about how we might go about doing this. And there's a lot of room to innovate and improve the methods that I'm going to talk about today. So I think this is kind of the start, I hope, of other work on this topic too. So the specific empirical example I'm going to be talking about today is going to focus on estimating internet adoption around the world. So just to motivate that a little bit, there's a lot of reasons why we think that there are important economic benefits to having internet access, but we know that there's a lot of inequality in access to the internet, both within and between countries. And being able to develop policies to help address this inequality requires being able to measure the rate at which people use the internet. And the kind of conventional approach to doing that is to conduct very rigorous in-person probability-based surveys. And that's a really great way to do that. But unfortunately, those surveys are often quite expensive and quite slow. And internet adoption is changing pretty quickly in a lot of parts of the world, and it'd be really useful to have a faster approach to trying to estimate internet adoption. And so today I'm going to try to explore an approach that can try to complement these slow and expensive but very high quality survey-based estimates. So in the big picture, I'm going to talk a little bit about the methods. Mostly the methods part is going to be sort of conceptual, and I'll refer you to the papers if you want to really see all of the details. And then I'll talk about the design of an empirical study in which we use some of the methods to estimate internet adoption in 5 different countries, and we'll go through the results of the study, and I'll talk a little bit about where I think this can go. This might be able to go next. Okay, so the big picture idea behind the methods I've already alluded to, which is that survey respondents are connected to other people through different kinds of personal networks. And we can ask the people we can easily reach questions about other people who they're connected to in these personal networks, and we can get information about more than just the people we interview directly. And so this kind of approach is not new. It's been used in a lot of different situations, including in demography, my home discipline. We use approaches like this to try and count deaths, which can be tricky to do in many settings. In epidemiology, this is useful for measuring the size of groups that are hard to reach in different ways, including groups like drug injectors and sex workers. You can use this kind of approach to try and study migrants, and there's many others. And there's a lot of different methods that have arisen in different literatures that use this basic idea of asking people to report about others. And I'm going to describe today this network reporting framework, which is a way to try to bring these different methods into the same kind of analytical framework. Okay, great. So how does this work? So let's say you ask people to report about others. How can you use that information to try and make an estimate? Well, I'm going to give you kind of a cartoon example to just give you the big picture ideas here. So this is an example of a small population that has 6 people in it. The 6 people are represented by these nodes in this network. And 4 of these people use the internet, and 2 of these people are on Facebook. And 2 nodes are 2 people, 2 nodes are connected together when they have some kind of relationship with each other. And I'm going to be vague right now about what this relationship is, but I'll talk about it, different possibilities in more detail a little bit later. But you can see that for our purposes right now, person 1 and person 3 are connected through some kind of relationship. When we ask people to report about others, these relationships, we can see the result of these reports as a sort of directed network in which one person reports about another. When one person reports about another, there's a directed arrow from the person who's doing the reporting to the person who gets reported about. So you can see that in this case, we've interviewed the people who are on Facebook, and there's now an arrow from person number 3 to person number 1 because person 3 includes person 1 in her reports. In general, there can be differences between this reporting network and the underlying social network. And the papers talk about that in detail. For most of today, I'm going to kind of assume that reporting is pretty accurate, but there's a lot of analysis in the papers about what can happen if the reporting is not accurate. So that's an important thing to keep in mind for sure. So it turns out to be useful rhetorically to take this reporting network and to transform it into this kind of bipartite format here, and to go to this right-hand side network from the left-hand side network. What I've done is I've taken the people who make reports and I've put them on the left-hand side, and then I've taken the people who could be reported about and I put them on the right-hand side. And now every single report leaves the left-hand side and arrives at the right-hand side. So the lingo I'll use is that these people on the left make out reports and these people on the right receive in reports. And you can see that from this picture that it's got to be the case that the total number of out reports that get made has got to be equal to the total number of in reports that are received. And we can actually take that identity and we can play with it a little bit to get an expression for the number of internet users in this case. So to see what I mean, so the total out reports should be equal to the total number of in reports. We could take this total number of in reports and we can factor it into 2 terms. One term is the number of internet users, and then one term is the average number of times each internet user gets reported. And then we can rearrange that relationship to solve for the number of internet users. And the expression we get says the number of internet users is equal to the total number of out reports about internet users divided by the average number of times each internet user gets reported. This quantity in the denominator here, I'm going to call the visibility sometimes because it's one way to think about it is that it's how visible internet users are. It's how many times they would be reported in a census of the frame population. Just to make this a little bit more concrete, let's look at this picture here. How many out reports are there about internet users? Well, this first respondent reports 2 different people who use the internet. So there's 2 plus the second respondent also reports 2 people who use the internet. So there's a total of 4 out reports about internet users. And then on average, if we go through the internet users here and calculate how many times each of them is reported, this first person's reported once, the second person's reported once, the third person is reported twice, and this fourth person is never reported. So on average, they're reported once each. And so if we take the total out reports 4 and divide by the average number of times each internet user is reported, which is 1, then we get the total number of internet users 4. So one way to think about this expression is that if we just added up the total number of reported connections to internet users, we'd get a number that was too big. And so to adjust for that fact, we divide by the average number of times that each internet user gets reported. So that's the kind of big picture intuition here. There's a lot of detail about how this approach is derived in the papers. But this expression is useful because it can form the basis for a sample-based estimator. And in order to get a sample-based estimator, we need to figure out how to estimate this numerator from a sample and this denominator from a sample. So I'm going to talk a little bit more about each of those pieces now. And I'll start with this numerator, which is the total number of reported connections to internet users. So in principle, this quantity is is not in principle too difficult to estimate from a survey. We can ask a respondent questions like how many people are in your network and which of these people uses the internet. If the responses to these questions are accurate, then we can estimate the total number of connections to internet users. But in practice, the challenge is that there's a lot of different ways we could tell respondents to define their network, and we need to pick one of these network definitions, one of these tie definitions to actually conduct our survey. And I actually think deciding on which tie definition you use is a really, really important design decision you make in one of these studies. So it's important to think through what the trade-offs might be in asking about different types of network ties. And so I'd just like to think a little bit about what we might expect here. And so I'm going to imagine what would happen if we asked about different types of social network relationships on a spectrum from relatively strong relationships. So that would be things like close friends, siblings, family members, etc. So that's one extreme. The other extreme would be very weak relationships, like acquaintances, people you might know to say hi to, but not really spend time with or ever talk to at any great length. And then there's a bunch of different types of relationships in between these two. And I'd like to think about how choosing ties of different strength will produce different types of errors in the resulting estimates. So one important characteristic of errors is related to sampling. And so from this perspective, previous social network research has shown that relatively strong tie networks tend to be small. So people tend to have a relatively small number of close friends, close family members, et cetera. And on the other hand, they tend to have a relatively large number of acquaintances or people they might say hi to without having a lot of deep interaction with them. And so from the perspective of sampling error, that suggests that there's advantages to asking about these weaker tie networks, because at least in principle, you can produce information about many more people from each interview by asking about these weaker tie networks. On the other hand, when you ask about these stronger tie networks, you only get extra information about a handful of people, and so the advantages from the perspective of sampling error are not as pronounced. On the other hand, from the perspective of non-sampling error, a lot of social networks research suggests that people will know a lot more about others who they're connected to through these relatively strong tie networks as opposed to these relatively weak tie networks. So just intuitively, I know a lot more about my brother or my close friends than I do about people who I pretty much only know to say hi to on the street, kind of thing, right? So that suggests that the reports that we get will be more accurate when they come from a relatively strong tie network as opposed to a relatively weak tie network. Now, at the end of the day, what we care about is the total error, which is going to be the sum of these two different sources of error. And so this framework kind of suggests that by varying the tie definition, we might be able to find types of network ties that produce optimal rates of error in some sense. Let me emphasize, this is a conjecture. I mean, I think there's a lot of reason to think that these curves have approximately this shape from previous social networks research, but this is a conjecture, so this is an empirical question that we're going to need to try and address. And so there's been a little bit of empirical work so far about this, and this has been a kind of productive way to think about these different ties so far. And the study that I'm talking about today included an experiment that was embedded in it to further test this question. And what that experiment did was to randomize respondents to report about one of two different possible types of network. So the first type of network is called the conversational contact network. And this is based on asking respondents, how many people did you have conversational contact with yesterday? Where conversational contact meant people you spoke with face-to-face for at least 3 words. So this definition comes from the literature in epidemiology, and it's been used to collect information about face-to-face contacts that are relevant for infectious disease transmission. So there's been some previous work that collects data like this, and that's how we picked this method. I think this is, and I think of this as quite a weak tie, because people you had some kind of face-to-face interaction with for at least 3 words is not a particularly high bar in terms of the social relationship. So the second type of network that respondents might have been randomized into reporting about is called the meal network. So this network is based on asking respondents, how many people did you share food or drink with yesterday? And then we specified that these could be all kinds of different people, and these meals or drinks could have happened in several different possible locations. And this network has also been used in previous studies, and the idea here is that this will on average, capture somewhat stronger type of relationship than people who the respondents just had conversational contact with. So we're randomizing respondents to report about one of these two different types of network. And the difference between these networks is that we think that the strength of the tie will be greater with the meal network. Okay, so let's suppose that we pick one of these definitions. How do we make use of the information that we collect? Well, we asked survey respondents a question like, how many people did you share food or drink with yesterday? And let's suppose that the respondent reports 6. I shared meals with 6 people yesterday. That response tells us about how big the respondent's network is. And in order to try and get information about what share of the respondent's network uses the internet, ideally we'd go through and we'd ask every single person in this network one after another. We'd ask the respondent about every single person in this network one after another. Like, do you think this person uses the internet? Do you think this person uses the internet, et cetera, et cetera. But the study that I'm going to show you the results from is based on conducting interviews on Facebook, and that's a very people have very limited attention spans in that context, and it's implausible that they would be willing to go through every single person that they reported having some contact with. And so we're going to ask people to select the first three of their contacts who come to mind, and we're going to call this subset the detailed alters. And we're going to ask for more detailed information about these 3 network members. So in the analysis, we're going to treat these 3 detailed alters as if they were a simple random sample of the respondent's network members, and that's probably not exactly the case. There's good reason to think that some alters might be more likely to come to mind than others for respondents, and we think about this assumption a fair amount in the paper. We describe how the results would be sensitive to this condition, and I'm going to show you some ways that we can kind of check all of the assumptions that we make together empirically. So, but this is one of the important assumptions that we make in our estimates. Okay, so that was a little bit about the numerator. Now let's think a little bit about this denominator, which is the average, the visibility or the average number of times each internet user gets reported. So you can imagine a lot of different ways to try to estimate this quantity. We chose a very simple approach, which is that we assume that people who have internet access don't pay attention to whether or not they're on Facebook when they share meals with one another. So to put that another way, we make the assumption that the rate at which people on the internet share meals with someone who's on Facebook is the same as the rate at which people on Facebook share meals with someone else on Facebook. So again, the paper discusses this assumption a fair amount, but the intuition is that if people aren't paying attention to who's on Facebook when they decide who to share meals with, then this assumption should be reasonable. And we can estimate the second quantity directly from our survey responses, and so that's the estimate that we're going to use for the denominator. So to put this all together, we estimate the numerator from the total number of reported connections to internet users based on one of the 2 different types of networks respondents were randomized into, and then we use the approach I just described to estimate the average number of in-reports per internet user. And our estimates are going to rely on 3 key conditions. The first condition is that the detailed alters are a random subsample of the respondent's network members. The second assumption is that people don't pay attention to whether or not they use Facebook when they decide whether to share meals with each other. And the third assumption is that reporting is accurate. And I put a star by that assumption because if you go through the paper, you'll see that it turns out that this assumption is not quite as strict as it might seem at first, because we're looking at a ratio of 2 quantities, both of which are estimated from these reports. And so if it's the case that there are reporting errors that affect the numerator and the denominator in the same way, then those reporting errors can balance each other out. And so it's not like every single report has to be 100% accurate for this to produce accurate estimates. It's that in aggregate, this ratio has to be accurate. And again, the paper has an analysis of what exactly that entails. And then I'm also going to show you some empirical results soon that will kind of give you a sense of how we can try to assess how well these assumptions are being satisfied in real data. Okay, so let's move on to the empirical results. Just to give you a little bit of information about study design, we obtained a random sample of Facebook users taken using Facebook's survey infrastructure, and we conducted a short survey that was taken either over the web or on a mobile phone. I looked at a lot of approaches to kind of calibrating and post-stratifying these responses, and we found that they mattered very, very little to the actual estimates. For the uncertain, I'm using a bootstrap that is appropriate for the structure of the survey data to estimate the sampling uncertainty of all the estimates that I can show you here. We had respondents from 5 different countries in our sample. So this plot shows the distribution, the age and gender distribution of respondents from each country for the conversational contact tie definition and the meal tie definition. Remember that respondents were randomized to report about one of these 2 different types of network. You could see that the kind of profile of our respondents is pretty similar to the profile of Facebook users in each of these countries. One other thing to note is that the sample from Great Britain is a little bit smaller. This was kind of like our pilot study, so you'll see that sampling uncertainty for the Great Britain estimates will be a little bit bigger in some cases. Okay, so there's results from 5 countries and 2 different tie definitions. So I'm going to kind of follow a pattern where I show you the results from one country and we walk through the plot together, and then I'm going to expand it out to see all 5 countries together so we can kind of understand what the plots are saying. So the first thing that I want to look at is the distribution of reported degree or reported personal network size from these 2 different tie definitions. And remember, we constructed the meal tie definition to be sociologically stronger than the conversational contact tie definition. So we're expecting the meal network to produce information about fewer people than the contact network, but we're hoping that the meal reports will be a little bit more accurate. So this shows the results from Brazil. In the top in purple, we have the distribution of reported conversational contact network size, and in the bottom in orange, we have the distribution of reported meal network sizes. And there's a couple of particularly salient things to notice here. So first, as we had hoped or expected, and this vertical line here is the average, is the estimated average across all respondents. So one thing to note is that as we had hoped or expected, the meal network is smaller on average than the conversational contact network. And then the other thing that we're going to quantify a little bit more in a second to note is that it looks like there's more kind of heaping or noisiness in this conversational contact network reports than there are in this meal network reports. So that's kind of a hint that maybe the reports from the conversational contact network are more kind of respondents' guesstimates than actual counts from the respondent. And if that's true, then that kind of suggests, as we would predict, that the meal reports are a little bit more accurate than the conversational contact reports. Again, we'll assess that a little bit more in a second. Okay, so these are reports from Brazil. Now let's expand out and look at the reports from all 5 of the countries in our sample. So this is the plot that we just saw from Brazil, and then here are the results for the US, Indonesia, Great Britain, and Colombia. And you can see that for all of the countries, the estimated average size of the meal network is smaller than the conversational contact network. And the suggestion of more heaping that we saw in Brazil seems to kind of hold in the other countries too. So it looks like it might be the case that, so it does look like the case that the meal networks on average are smaller than the conversational contact networks. And there is this hint that maybe the conversational contact reports are a little bit noisier. But how can we kind of make a little bit more progress on really understanding whether one of these ties is producing more accurate information than the other? That's the basis for these internal consistency checks. And the idea here is to come up with 2 independent ways to estimate the same quantity from these network reports, and then to compare these independent estimates to one another. And if all of the assumptions that we've made are satisfied, then we would expect these 2 estimates to agree up to sampling noise. But if these assumptions are violated, then that may result in these internal consistency checks not agreeing. So just to make that a little bit more concrete, for both of the networks that we're looking at, the number of connections between men and women has, in principle, at the population level, has to be equal to the number of connections from women to men. Because every time a man shares a meal with a woman, that means a woman also shares a meal with a man. That's a property of these 2 networks that we're using here. So what we can do is we can calculate the estimated total number of reported connections to women made by men, and the estimated total number of connections by men made to women. And these 2 estimates come from entirely different data, right? This estimate here comes from the survey respondents who are male, and this estimate here comes from the survey respondents who are female. And we can, so If all of the assumptions are met, then the difference between these two estimates should be 0 because they're the same, plus or minus some sampling noise, right? And to the extent that that difference is not 0, then that's some kind of signal that there's some extra sampling. There's some error beyond the sampling. Okay, so this plot shows the results of these internal consistency checks for age and gender groups from the survey in Brazil. And the results from the conversational contact definition are these purple points, and the results from the meal network are these orange points. And just to make this a little more concrete, you can see that this point here is plotting the meals that everyone else reports sharing with young women, minus the meals young women report sharing with everyone else. And in this case, the confidence interval, which is based only on sampling noise, includes 0. And so this is consistent with reports being pretty good for this group. On the other hand, if we look over here at young men and the conversational contact network, it looks like young men report more connections to everyone else than everyone else reports to young men. So this is kind of some indication that something has gone wrong in our assumptions somewhere, because if all the assumptions were perfectly met, then this interval should include 0. Okay, so sort of like before, this is the picture for Brazil. I just showed you the picture for Brazil, and now we're going to look at the picture for all of the countries together. And you can see that in many cases, these confidence intervals do include 0, but there are some notable examples where they don't, which suggests that there's some reporting error. This is particularly true in Colombia and Indonesia among young people. So that's something that we need to be aware of when we interpret our results. And it's also something that we can use to help improve the method in the future. I'll talk about that a little bit now. So these internal consistency checks are really, really useful, because to make estimates from this kind of method that I'm describing, we have to make a lot of assumptions. And this is a way to kind of give us a sanity check for the data that we actually collect. Like, how reasonable are these assumptions in this case? But in addition to detecting where there appears to have been some kind of violation of the conditions, we can also use these internal consistency checks to compare which of these two tie definitions is more accurate. So remember, respondents were randomized to report about either the meal or the conversational contact definition. And the reason to do that was that we think that there's this trade-off at play between the non-sampling and the sampling error. But it's really only useful to think about that trade-off if we can improve over time in the type of network that we ask people to report about. So it's important that we have some way to assess from data that we've collected which type of network relationship seems to be producing more accurate information. So all of this is kind of important to helping to fill this picture in over time. So this shows the estimated difference between the internal consistency check accuracy for the results from Brazil. And so when the estimate is to the right of so at exactly 0, there's no difference in the estimated internal consistency check values from Brazil, from the conversational contact definition and from the meal definition. To the extent that the mass of this distribution is to the right of this 0 line, that implies that the meal network is producing more accurate estimates. And if it were to the left of this line, that would imply that the conversational contact network is producing more accurate estimates. So you can see that in the case of Brazil, it looks pretty clear that the meal definition is producing more accurate estimates than the conversational contact definition. And when we expand out to the other countries, that's true not only in Brazil, but also in Colombia and in Great Britain. It's a little bit less clear in Indonesia and the US which of the two networks is producing the more accurate estimates. It's not as conclusive in that case. Okay, so what's the takeaway from the internal consistency checks? Well, I really like these because they're a built-in way to kind of sanity check the results that you're getting from one of these studies. And I'm arguing that it's particularly useful for building up a picture of what kind of networks people can accurately report about. We see some evidence of reporting error, especially in Indonesia and Colombia, which might be suggestive of differential social visibility. And then to kind of go beyond what we're doing in this paper, in the future, these IC checks could also form the basis for some kind of model-based approach to producing estimates from these data, because they give you these relationships that really should be satisfied if the reports are accurate, and there's some information there that can be used to try and help improve estimates from these reports. And then more empirically, we see that at least from these 5 countries and 2 networks, it looks like the meal network is somewhat more accurate, at least for those 3 countries that I mentioned in the previous slide. Okay, so what are the actual estimates that we see here? Well, this shows the resulting estimates of internet adoption in 2015 from the Conversational Contact Network and the Meal Network. And there's a few kind of important takeaways here. So the first is that the 2 types of network relationship produce very similar estimates. And the kind of order of these countries is more or less what we'd expect, given the country's GDPs, for example. And the sampling variation does not look like it's particularly important here. At the sample size that we have, the sampling variation is not super big. And that's because for both of these approaches, we get a lot of advantages from having people report about others. That kind of inflates our sampling accuracy quite a bit. So non-sampling error is what we're more concerned about in general. So ideally, we'd be able to compare these estimates to a super high quality probability sample or census data. We were only really able to do that in 2 places, the US and Great Britain. And so this plot shows the estimates from these alternate sources. So in the US, we have a Pew survey, and we have a survey from the ITU. And in the UK, we have, in Great Britain, we have an Ofcom survey and a survey, and also a survey from ITU. The ITU estimates are actually repackaging of the Census Bureau estimates in the US and the Eurostat estimates in Great Britain. So these are kind of high quality alternate estimates. And you can see that the results from our study are mostly in line with those, especially for the meal definition. I should say this slide has not been updated, but the paper also has a comparison estimate from a survey in Brazil. And in Brazil, our estimates are a little bit higher than the comparison estimate, but I think still within the sampling uncertainty of the comparison estimate. So we can't directly assess these estimates everywhere to some kind of gold standard, but comparisons to other estimates in the US and Great Britain suggest that our results are similar, maybe a little bit low. And the internal consistency checks revealed that there's some evidence of reporting error. The reporting error is something we might be able to make some progress on by building models, but actually I think the best way to minimize that reporting error over time is to keep collecting data with different types of high definitions and to try to zoom in on the type of network that people seem to be able to really accurately make reports about. And I think part of the contribution of this paper is to show how we can do that, right? We can use these internal consistency calculations to try and figure out which high definition is more accurate. And the hope is that by kind of iterating over time, we can zoom in on types of networks that people can report accurately about in this kind of survey. And then there's a lot more detail in the paper, including a sensitivity framework that kind of helps to quantitatively assess how sensitive the estimates are to the different assumptions that we've made. So where might this go in the future? Well, so as I've already said, I obviously think that filling in this picture is pretty important. And there's been some work on this so far. So there's a network scale-up study in Rwanda where my colleagues and I compared a relatively strong network to quite a weak network over a long time period. So this is asking about interactions over a year, which seems a very long time period. Then in this study that I just showed you, we looked at interactions in the previous day through a relatively strong and a relatively weak type of network. There's another study in that's kind of the paper's getting written up, a scale-up study in Hanoi, Vietnam, where there's a combination of long and short time windows and also different high strengths. And then maybe someone here will conduct a study that will help us fill in some of the rest of this landscape. What we really need to understand is empirically how what sort of trade-offs are at play when we pick different types of ties to ask respondents to report about. And if we can figure that out, I think that'll make a big difference. And then more generally, if we think about the big picture problem that I started motivating the talk with, what we did today, what I showed you today is we started with an online sample and we produced an estimate that was fast, inexpensive, high time resolution in the sense that we got information about the day before the interview. And because it was conducted online, it's very easy to build experiments and that kind of thing into this type of study. Let's think for a second about how that compares to a conventional probability sample. So the estimates that we get from a conventional probability sample are pretty expensive and come fairly slowly. but they're very high quality. And critically, the network reporting framework reveals that there's some information we could collect in a conventional probability sample to try and help improve the quality of online estimates. So I actually think the best of both worlds is possible here. You can imagine rarely conducting a conventional probability sample, which would be expensive and time-consuming to conduct. But that probability sample could collect information that would allow us to kind of tune estimates from these online samples over time. And the hope would be that that combining these two different types of surveys would produce more accurate estimates with advantages from the advantages of the online sample, like the timeliness and the ability to experiment, et cetera, et cetera. Actually, if you think about it, this is not so different from, you could draw a picture like this where here we have the population census and the conventional probability samples are what get taken in between censuses, often heavily relying on the census for the sampling frame and information that's used in weighting and so forth. And so this is kind of like the relationship between the population census and the conventional probability samples, but at a different time scale. So instead of having a census every 10 years, you can imagine having a conventional probability sample every year or two, and then online samples filling in between. Okay, and then I have a lot of other, I've thought a fair amount about these network reporting methods, and so I have a few other projects that might be interesting to folks. I'd be happy to talk about this in the questions. But in addition to kind of using an online sample to learn about more than just people who are online, you can also use this approach to estimate death rates and migration rates in different settings. You can use it to try and understand the size of these groups that are epidemiologically important, et cetera, et cetera. So just like to thank my collaborator. You can check the paper out online. There's a couple of R packages and some related papers there too. I'd be happy to answer any questions or talk about this more.